Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on measurement of acoustic signal. As usual, before we enter the study of today's lecture, let me give you a quick review or overview about the answer to these four common questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to learn from this course? And the question number four, how to learn the knowledge. All right. So let me start with the answer to the first common question, which is about the why to study this course. By now, you should know that our mission on Earth include, number one, to understand the world through the use of sensory data. And the number two is to improve the world or change the world through the incorporation of a closed-loop control system into the design of a smart product, smart machine, smart system, all right? So in order to understand the world, we need to discover knowledge, okay, through the use of sensory data. Then how to obtain sensory data? The answer is to make use of measurement and the sensing system, all right? Then in order to improve or change the world, we need to invent a smart machine, smart product, smart system, which will incorporate closed-loop feedback control system inside. Then what is a closed-loop feedback control system? The answer is it is a system with three basic building blocks or three basic building modules. One of them is a sensor. All right, so therefore you understand that this course is extremely important. All right. And from this slide, you see the future city may include the presence of smart parking systems, smart building system, smart street lighting system, smart home system, smart environmental system, smart healthcare system, and also Internet of Things, right? And inside the Internet of Things, there are two basic devices. One of them is a sensor, all right? Second common question that you may have in mind is about how to study this course, all right? So my recommendation to you is to put yourself into the mindset of a designer. Then with the keyword of a design or designer, automatically you will ask this question, who are the user, what are the needs of the user, what should be the functionality of the product or system that you are going to develop, then what should be the solution behind the design of your product or your system, all right? So the answer to question number one should be obvious to you because these users include ourselves and the smart product, smart machine, and the smart system. Answer to the question number two should be obvious to you as well because all these users have this common need, which is to have sensory data, right? Answer to question number three depends on the nature of the user. For example, smart vehicle may need to have a certain type of sensor, and the smart robot may need to have another type of a sensor, right? The answer to question number four is to study well this course, okay? At the end of the study of this course, you will know the solution behind the design of your product or your system in terms of a sensor, Internet of a sensor, or measurement and the sensing system. All right. And question that you may have in mind is about what are you going to learn from this course? Basically, this course will cover the study of basic knowledge, okay, behind the design of a popular sensor in electric domain, mechanic domain, environmental system, and the intelligence system. In addition, this course will teach you the basic detail about the physical world, the basic detail about the conceptual world, all right? Also, this course will teach you the basic knowledge for you to cope with the randomness in the physical world and for you to understand fuzziness in the conceptual world. By now, we have already completed the study of the physical principle behind the design of a popular sensor in electric domain, in mechanic domain, and in environmental system. Now we move on to study the tool important measurement and the sensing system for intelligent product, intelligent machine or intelligent system, right? And you will understand that the two pillars on the human intelligence or machine intelligence are the capability to transform visual signal into knowledge and voice signal or speech signal or acoustic signal into knowledge. So then you will see the measurement of acoustic signal in terms of sound or audible acoustic signal, and the measurement in terms of visual signal are extremely important, not only to human intelligence, but also to machine intelligence, right? And the fourth question that you may have in mind is about how to apply learned knowledge from this course, right? So basically, you are going to apply learned knowledge to guide the design of measurement and the sensing system, right? The design of a measurement and the sensing system will involve two steps. Step number one is to transform the value on the measurement into readable value. Step number two is to calibrate your measurement and the sensing system so that the value from the output is exactly equal to the value at the input. In addition, the unit of a measurement assigned to the output will be the same to the unit of a measurement at the input, right? Then for step number one, you may face two cases. The first case corresponds to the situation in which it is good enough for you to just make use of front-end sensing element in order to transform the value on the measurement into readable value. However, in most cases, you may face the situation in which you must make use of at least a series of two sensing elements in order to transform the input value into readable value, right? So these are the general guidelines for you to follow in order to apply learned knowledge from this course, all right? So now we are ready to move on to study today's lecture, which is about the measurement of audible acoustic signal, right? So as I mentioned just now, two pillars underlying human intelligence are these two mental capabilities. One is to transform a visual signal into knowledge. The second one is to transform audible acoustic signal into knowledge, right? So similarly, these two mental capabilities should be the two major pillars underlying machine intelligence. Therefore, so you understand that the measurement of acoustic signal is extremely important, all right? So it serves as a foundation for you to venture into further study about the speech recognition and the speech understanding, right? Then for this lecture, so we start with the basic physics and the mathematics behind acoustic signal. Then we move on to study the way for us to undertake a computation with acoustic signal. Then the major focus should be the direct measurement of acoustic signal, all right? Let's begin with basic physics behind acoustic signal and also the basic mathematics involved, okay, with acoustic signal, all right? So now you understand acoustic signal enable human being to undertake a conversational dialogue. Without such mental capability, it is not possible for us to talk to each other, for us to attend lecture, for us to attend tutorial, for us to watch movie, for us to watch TV, or attending meeting, etc. So you see, this is extremely important mental capability for human being, but also for machine, because in future we may want to let robot to work together with us. Then you understand if robot could be instructed with the use of a human language, then it will be extremely easier for our life, because write the program for a robot to perform is much more complicated than just talk to a robot, because every one of us how to know how to use our own language. If robot could master human language, then it will be easier for us to instruct robot about what to do by the robot. All right, so this is a very important application. All right, besides the conversational dialogue among the people or between robot and the people, all right, we can also find many applications in industry, okay, with the use of acoustic signal. And this video show you one example.
Alexa, tell the pump to turn on.
Turning pump on now.
Alexa, tell the pump to turn off.
Turning pump off now.
So the way this all works is,
all right, so you see, then application with the use of acoustic signal in robotics. Okay, so
projects. Bad robot. Good robot. In addition to this,
all right. And in transportation and in future, eventually we can talk to our vehicle, all right? So,
send the meeting address to my Volvo. Start the heater in my Volvo. Prepare my Volvo.
all right. We can also find the important application with the use of acoustic signal in medical field. All right, so this video show you the scenario.
When discussing ultrasound-guided peripheral nerve block technique, it is useful to describe basic nomenclature for needle and probe manipulation. Much of this is derived from the American Institute of Ultrasound in Medicine standards. We will describe the 2 basic scan planes, the 5 probe manipulation maneuvers, and the 2 needle approaches. In the following figures, we are looking at a schematic of an ultrasound transducer applied to a tissue equivalent phantom with 3 different embedded objects. A depiction of the ultrasound screen is inset. We generally image long cylindrical structures with an ultrasound beam that is essentially planar. Short axis imaging cuts this cylinder transversely, revealing a circle. Long axis imaging cuts this cylinder longitudinally to create 2 parallel lines. Long axis imaging is of limited use in ultrasound-guided peripheral nerve blocks. An ultrasound transducer can be rotated or translated along any of its 3 axes. Hence, we need to use the AIUM standards so that we can communicate clearly with one another. Here we see an ultrasound probe moving and pivoting along each of its X, Y, and Z axes. Each of these movements has a name that we will define in the next section. Sliding is a maneuver that translates the transducer along the course of its structure, or perpendicular to it to scan adjacent structures. Compression is a useful maneuver that has numerous effects. First, it moves the active face toward deeper structures to make them appear more superficial. It also helps differentiate between different structures by their relative compressibility, Veins are easy to compress, arteries are somewhat compressible and pulsatile, and nerves are fairly incompressible. Rocking allows us to extend the plane of imaging when we are working in a narrow acoustic window. Rotation is used to switch between short axis and long axis imaging. Tilting allows us to scan along the course of a structure through a narrow acoustic window. In nerve imaging, it is critical to optimize transducer tilt to properly visualize nerve fascicles. Nerves are seen best when the scan plane is orthogonal to the course of the nerve. Given that we are most interested in nerves imaged on short axis, we will now look at how the needle will be seen as it approaches nerves. With the out-of-plane needle approach, the needle starts in front of the plane of imaging and advances until it crosses the plane of imaging as an echogenic dot. With the in-plane needle approach, the needle is visualized on its long axis as it advances within the scan plane. Now let's move on to show some of the common challenges with visualizing the block needle sonographically. Block needles are specular reflectors, meaning they reflect sound back to the receiver over a narrow angle. As the angle between the transducer and needle increases, less sound is reflected back to the receiver, and the signal becomes weaker. We can also see that this is true for sound reflected off the sides of the needle shaft. With the short axis out-of-plane approach, the needle will be seen best when the tip is within the plane of imaging. The shaft gives a signal that...
All right, so this gives you a rough idea about the application with the use of acoustic signal in. And here is one more example of video for you to understand the important application in medical field.
Sound guidance for vascular access. We're going to be using a linear ultrasound probe to guide the positioning and placement of this needle to gain access to a vein, artery, or any other vascular structure that you need to get access to in a quick and fast, efficient means without jabbing your patient multiple times. Put your transducer on the patient's skin, center the image, the vessel, in the center of the transducer face. We have multiple crystals across here. We're going to center the vessel directly under the transducer center so that when I enter the skin, I'm going to hold the transducer at an angle, I'm going to hold the needle at an angle, and hopefully they will meet at a point near the vessel in the center of the image. I'm going to keep advancing it until I see the needle show up in the image. I want to come in at a fairly low angle so that I can see the needle show up in the image above the top of the vessel. I don't want it to already be through the vessel. I don't want it to be below the vessel. I want to see it on top of the vessel because then I can position my needle right or left to put it directly over the top of the vessel itself. Once I'm directly over the top of the vessel, all I have to do is angle up and enter the vessel. By moving the transducer with the tip of the needle, I can follow it as it goes until I actually see it penetrate the vessel wall and enter and end up being cinder lumen on this vessel. And what I'm doing is entering the skin, looking for my needle to show up in the image, above the top of there it shows up. You can see it right there as I advance and back it up. That's the tip of the needle. And you can see I'm not exactly over the top of the vessel. So by angling the needle sideways, I can now advance the transducer, advance the needle. I can angle it over a little bit more and advance the transducer. Advance the needle, advance the transducer. Advance the needle, and then the transducer until I'm right on top of it. Now that I'm right on top of it, I'm actually pressing on the vessel itself. All I have to do is bring the hub of the needle up a little bit. And we're now in the vessel. At that point in time, I can now put the transducer down, disconnect the syringe. You can do this without a syringe. You can look for your blood flash right here. I can thread my wire if I'm going to do a PICC line. If I'm going to be doing a venous ablation, I can get my guide wire in. Once the guide wire is in, pull the needle out, hold your guide wire, put in your introducer sheath right along the same pathway, and you've got instant access. So for vascular access, again, transducer, 90 degrees, vessels in a short axis, bevel up, enter at a very steep angle till you see the needle over the top of the vessel. Then all you got to do is turn once you get over the top of the vessel, angle up and follow that needle with the tip of the transducer. It's two-handed. You're advancing both needle and transducer at the same time, following the tip of that needle until it enters the vessel. Once it enters the vessel, you get your flash, you get put in your guide wire, and access is there.
Right, so you see, these are the quite interesting application with the use of acoustic signal. Of course, there are many other applications such as speaker identification, measurement of the distance, and monitoring the health condition, etc. All right, so you will see acoustic signal is very important to the development of a smart product, smart machine, and a smart system. All right. So here is one more example showing you the application with the use of a sound signal. Sound signal means audible acoustic signal for the support of a conversational dialogue. Then in this case, we have a speaker in the left-hand side, we have a listener in the right-hand side. Then you will see the transformation of acoustic signal from source all the way to receiver, all right? So then you see the measurement of acoustic signal is very important because once we are able to measure acoustic signal, then eventually we can transmit the acoustic signal over long distance or wirelessly so that the speaker and the listener can overcome the distance limit. That means one person could be in Singapore, another person could be in Europe, all right? Then these two persons could undertake a conversational dialogue with application, okay, of this scenario, all right? Then, okay, our focus here for this lecture is on the measurement of audible acoustic signal. Okay, audible acoustic signal means sound, all right, or voice, all right? Then how to understand the voice. So basically, we need to focus on these three items: source, receiver, and the path, all right, or the space, okay, for the signal to go from the source until you reach the receiver, all right? So then it is easier for us to understand the property and the nature of the sound, all right? So how to produce audible acoustic signal? Then you will see our handphone, our car, and the speaker, and even human being, musical instrument, etc. All these are the potential source of sound or audible acoustic signal. I guess every one of you are familiar with the source of sound, all right? And in addition, the air graph during the conversation among the people, all right? So they will also produce a sound, and the sound basically means what is a mechanical vibration, okay, in air, all right? And this vibration is a periodic vibration, all right? And then immediately we understand if we apply the knowledge about the Fourier transform, all right? So sound signal basically is the sum of a pure sine function, all right? And each source of sound will basically produce the sum of a sine function, all right? So you understand in this way, all right? And here is an example showing you the sine wave, all right? So actually you see sound is being produced by mechanical vibration, because mechanical vibration will produce a pressure wave, all right? So this is the nature of the sound. So you see the pressure wave. Pressure wave means there's a periodic variation between condensation of the air and the rarefaction of the air. So it means there's alternating value of pressure in air, right? From the lowest value to the highest value, okay? Negative peak, positive peak, or crest, and the trough, right? Trough means the lowest peak, and the crest means the highest peak, right? So then you see this is a pure sine waveform, right? And then this is also for you to know, okay? Sound is a pressure wave, right? So besides pressure wave, we also have a stream wave. For example, the light or electromagnetic wave are stream wave. Electromagnetic wave are not the pressure wave, right? So these are the two typical type of a wave. So sound wave is a pressure wave, all right? So without the media, the sound wave could not be transmitted out. So you need to have a media, right, in order to generate variation or alternating pressure, okay, inside the media for transmission, right? And this slide basically showing you one more example about the nature of pressure wave, right? So you see we have an area of a high pressure, area of a low pressure. And if we draw the magnitude of the pressure from low to high, and also look the time variation, so basically you see a sine wave, all right? So it means sound wave is a sum of sine function or sine wave, right? So that's about the source. Now, how about the path? How will the sound wave travel in space or travel inside the media, such as air or water or other type of material, right? So basically, the sound source can come from everywhere, because we can position the sound source everywhere, right? So the starting point of sound source, okay, or the sound wave could be anywhere in the space. So that is the starting point, okay? It could come everywhere. Then once the sound wave exit from the source, then it will travel along the straight line until it will hit object or hit the surface, then it will bounce back or reflect in other direction, okay, such as in the symmetric direction about the normal of surface, right? So in this case, you will see this wave will hit the wall, then reflect back, then hit the wall again, then reflect back, then finally enter the ear of the receiver. Our ear basically is the receiver channel, right? Then for this one, hit the wall, then hit the wall again, then enter the ear of the listener, right? So if there's no other surface in the path of a sound wave, then the sound wave will travel continuously, right? Okay, so it will travel continuously by following the straight line, okay? And another phenomenon is quite important for you to know, which is about the interference, because you have a multiple source of sound. Then we have a multiple wave, okay, which could intersect together When they intersect, then there's interference will occur. And in general, there are two typical interference. One is called as a constructive interference. And then in this case, the peak value will be added up together. So this is the typical situation for these two sound wave to be aligned together. So positive peak aligned with a positive peak, okay? Negative peak aligned with a negative peak. Then this is a constructive interference, all right? However, we may have this situation, all right? So the phase shift is 180 degrees. So it means positive peak of one sound wave along with a negative peak of another sound wave, A together they equal to 0. Then we have this zero signal, all cancel out, all right? So then in this case, we call it as a destructive interference. Then in most cases, okay, so the interference should be weighted sum of these two, right? So if they are not exactly in phase, if they are not exactly out of a phase, right? So then, there will be a variation, right? In different way, right? Okay, so here's one more example. Let's say we have a two source of a sound, okay? Then you will see at this physical location, there will be a destructive, interference at this location, destructive interference. Then at this location, there's a constructive interference, right? So this is quite straightforward for you to understand, all right? So another phenomenon is when we have a two sound wave with quite close frequency, for example, like our speech, all right? So our mouth throat can produce multiple sign function. Then when all these sign function A together, then this should be the final sound wave, all right? So then you can imagine the frequency for all these sine wave should be quite close, John. We cannot produce two frequency with a big difference, all right? So then in this case, you will see this phenomenon, all right? So when you add them together, then the final signal appear like a series of a beep, okay, series of a peak. So actually, when you see later on, I will show you the example of a voice signal. So more or less, it will look like this, all right? So now you understand the reason. This is because the sine wave will have a similar frequency. All their frequency are quite close to each other, okay? So this is a typical example showing you this phenomenon, right? And another property for you to know is this is not like a vision system, okay? Sound wave is one-dimensional signal. However, we can put the multiple receiver together to form a vector or eventually to form a matrix, all right? So in the video about the medical application, then you see the transducer actually is a vector of receiver. So therefore, we can construct a two-dimensional image, right? So if we look at the single source, actually is a one-dimensional time signal, right? And this video showing you our ear's impression, okay, in response to different frequency, okay. The sound come up. Okay, we can stop here because once the frequency goes higher, our ear we are not feel comfortable. All right, so you see, so different frequency, then our perception, okay, acoustic perception start to change. So you will see the sensation of sound is a function of frequency. All right. And then, okay, this is a typical example of a sound receiver. We can use our ear because everyone of have two receiver like this because we have a left ear, right ear, all right? So our ears are a receiver of a sound wave, all right? So we may also have a microphone channel. You may have heard of this technical term, a microphone. Basically, microphone is a receiver of a sound wave signal, all right? So let me show you example. This is a receiver. Then we eventually can amplify the sound wave signal, then playback with a speaker, all right? So we can reproduce the measuring the sound wave, okay, with the use of a speaker. So this is a typical example for you to know, okay? So we can capture sound wave, then do the processing, then we can play back, okay, the sound wave signal, all right? Now we try to understand, okay, just now already understand the receiver, all right? So then this is another property about the receiver. When receiver receive nothing, we cannot make this conclusion that there is no sound wave signal in the space, right? Because the receiver may at the special location in which there is a perfect destructive interference, okay? Then in this case, there's no signal. Once you change the position of the receiver, then signal will appear, all right? So when we hear nothing, normally we should not make a conclusion by saying that there is nothing, okay? So actually there's something there, but somehow the interference make the signal to have a zero amplitude. That's it, okay? It does not mean the frequency is not there. There is a frequency, but the amplitude is zero. That's it. It's not totally empty, all right? And when the sound source move or the receiver move, then there is this Doppler effect. Okay, so we have a study this effect in one of the previous lecture. Okay, so basically when the sound source approach the receiver, frequency will increase. The perceived frequency will increase. When the sound source receive from receiver, okay, or increase the distance from the receiver, then the frequency appear, okay, to be reduced, right? So this is a perceived frequency, and this slide shows you the equation now, right? So when the source approach receiver, the frequency will increase, and when the source receding from the listener, okay, then the frequency will reduce, okay? So these are the formula for us to determine what should be the perceived frequency if we know the relative velocity, okay, from the moving source, okay, to the listener, right? So this is mathematics behind this phenomenon of Doppler effect, okay? So we need to know, okay, what should be the parameter, okay, which are related to the description of the sound wave signal. So actually the answer is similar to the case of a vibration, because we know, okay, we have done the study about the measurement of a vibration, right? Vibration will produce a periodic signal, and this signal are described with the use of a sine wave function, right? Then for this special signal, for example, audible acoustic signal, all right? Because audible acoustic signal are also the result of a mechanical vibration. So therefore, the description of a sound wave signal should be the same. So basically, we use the combination of a sine wave function to describe, okay, sound wave signal, right? And in each sine function, we only have 3 parameters: amplitude, frequency, and the phase shift. So actually, amplitude and the frequency are the 2 most important parameters, right? Because amplitude is a measurement about the energy, and the energy basically refers to loudness or level of loudness of the sound, all right? And the frequency distribution may give us this technique description in terms of sharpness, right? If the distribution is quite narrow without the other mixture of noise, the frequency, then we may feel that the sound is quite sharp, okay? There's no other background noise, etc., right? Then roughness is about the amplitude, the fluctuation, right? So you may have a loudness, okay, uniform loudness, all right? Or you may have a fluctuation of amplitude that gives us impression about the roughness. It's like when you drive your car on the surface, on very rough surface, okay? Then you will see the vibration, okay? The lack of smoothness, all right? Then fluctuation strength basically is about the measurement of roughness below 20 hertz, all right? Then for voice, because voice allow us to decode meaningful data, okay? Because when we talk, okay, we must speak in English, speak in Chinese, etc. Basically inside our voice, there's information there, okay? So then how easier for us to decode, okay, meaningful data? So that is a measurement about the intelligibility, all right? So degree of being comprehensive. If the our speech or our voice mix up with background noise, then we will lose, okay, the level of intelligibility, right? And the tonality basically refer to the pattern. You can combine, have a specific combination of frequency, specific combination of amplitude that create a pattern, okay? So that pattern is called as a tonality, all right? So these are the indicators for us to evaluate the quality of the sound, all right? So this should be the post-processing, because for this lecture, our focus is on the measurement of a sound wave signal. It's not on the compute or processing or post-processing, okay, of sound wave signal, all right? But it's just for you to know, all right? So based on this lecture, you can venture into the study of evaluating sound quality, etc. Right? And what is energy? Because when we speak, when we talk, okay, we may have a very loud voice or very soft voice. Okay, soft voice means what? Less energy. Very, very loud voice means what? A lot of energy, okay, coming out from our mouths, all right? So energy here basically means energy per unit spheric area, right? So the spherical area basically is a function of a distance from the center of the sphere, right? So when the sound propagates into the space, longer the distance and smaller the loudness is because the distribution per unit spheric area will reduce because with same amount of energy power, okay? If you divide it by larger area, then the loudness will be smaller, right? And in order to match the sensation of a human ear, so actually our ear is not linearly related to this value, okay? Our ear's sensation is linearly related to the logarithmic function of a power, all right? So then we use this to indicate the level of loudness, and they use this unit of measurement, which is called decibel, right? So in layman term, we usually use this unit of measurement, dB, right? And this slide basically showing you the level of loudness, okay, when we talk among ourselves. So it's 62 dB. When you see a motorcycle pass, move on the street, okay, pass by you, then the level of loudness is 98 dB, all right? Then you may see the jet, okay, the fighter, the airplane take off or pass by in the sky. Then you see the level of loudness is 133, and you see it's very loud and noiseless, okay, in the sky. Then you will see this is the level for our ear to start to feel uncomfortable, to feel pain, okay? If the level of loudness exceeds 125 dB, right? So this is just for you to know, right? So all these are related to amount of energy per unit area, right? And then since there are two important parameters, okay, inside the description of a sound wave. One is amplitude related to the amount of energy, when the energy exceeds certain level, then our ear will not feel comfortable, right? Second one is about frequency. And similarly, when the frequency is too low or too high, then our ear will never respond. Okay, so this is why we have these three type of interval, right? So between 20 Hertz and 20 kilohertz, then all the acoustic signal should be audible by our ear. That means our ear can perceive, right? If it is below 20 Hertz, then we call them as infrasound. Okay, then our ear will not produce response. Or go beyond 20 kilohertz, then our ear will not have any response. All right. So this is why we use this layman term sound to refer acoustic signal within the frequency range from 20 Hertz to 20 kilohertz. All right. So for human-robot interaction with the use of a voice or conversational dialogue among the human beings. So basically, we will make use of a sound signal. Okay, we are not going to make use of infrasound or ultrasound. However, you will see machine could make use of infrasound or ultrasound to undertake a conversational dialogue among the machine themselves. Okay, this could be a useful application. For example, for certain type of machine, we do not want the human being to listen to their conversational dialogue. All right. For example, military robot in the front line, when the robots start to talk to each other, then the enemy may not hear the voice. So this could be a solution, okay, for certain type of communication. In certain situation, we do not want the human being to hear the conversational dialogue among the smart robot, smart vehicle, or smart machine. Then we need to use ultrasonic sound, ultrasound, or infrasound. All right. Then in this case, even we are there, we do not know what they are doing, because we hear nothing. All right. So this knowledge basically is useful for you to apply, okay, in order to implement specific application, right? And besides frequency range, of course, we also have amplitude range. What should be the range? Then, as I said before, when the range exceeds 125 decibel, then human ear will not feel comfortable, right? However, for machine, they don't care, if let's say this is for machine to undergo conversational dialogue, then this is not an issue, right? So this is the issue to human being, but not to machine, all right? So it's good for you to know. This slide basically showing you the typical pattern of voice. So you see is a series of a beat. So you see in this slide, we are already telling you when the frequency of sine function inside sound signal are very close to each other, and the signal will appear to have a series of a beat like this. Now, when we pronounce happy birthday to you, then you see it's like a series of beat, right? So we can speak happy birthday to you, or we can sing happy birthday to you, or something like that, all right? So you see, this is the time function of our voice, right? Of course, we can do Fourier transform because now you know, okay? Once you have a time function, we can apply Fourier transform to discover the frequency and the amplitude, okay? Inside any signal, because any signal is the sum of a sine function. Then sine function has amplitude, has frequency. Then at each time, okay, we can discover the series of frequency present, okay, and use color to indicate the value of frequency. From low blue means a low frequency, and yellow, okay, or white color because a high frequency. All right. So at each time we have a series of frequency of a different value. So then if we display them together, then we have an image, okay, showing you the distribution of a frequency across the time. All right. So this is a typical example showing you that you can undertake post processing, okay, after the measurement of acoustic signal. But this lecture will not focus on post-processing because you need to study signal processing courses that will take 1 semester for you to follow. All right. So this just to indicate to you, okay, with the digital data of sound signal, then you can do a lot of things, including signal processing, etc., speech recognition, speech understanding, etc. All right. So this just help you to see the usefulness of sound signal, right? And this is also for you to know, okay, how do we transmit out capture the sound signal over long distance? Solution is to modulate the carrier signal. Then at the reception side, then we demodulate the carrier signal. Then we cover the sound wave signal. So this means after the measurement of sound wave signal, right, we can use a carrier signal to do modulation. Then in this way, through the wireless communication or wired communication over a long distance network. All right, so it's just background knowledge for you to know, okay, how to transmit out the sound wave signal in space or over long distance, etc. So we can also modulate, okay, amplitude. So this is to modulate frequency. In carrier wave is fixed frequency. Then we can use the time signal, okay, the value of the sound signal at each time to modify the frequency, right? And then this is an example. If let's say these are the amplitude, then we can increase this amount of frequency, reduce this amount of frequency. Okay, so based on the frequency change, then we can recover the amplitude of sound signal in time domain. All right. We can also modulate the amplitude of a carrier signal. Right. So if the sound signal appear like this, then without the modulation is horizontal line for the carrier signal. Then after modulation, then you see the envelope of the carrier signal is more or less looks like wave, sound wave signal, right? So these are the way for us to do the modulation in order to transmit out the sound wave signal over long distance. Okay. So that's about the basic physics related to sound signal or acoustic signal and audible range, and also the basic mathematics behind the description of sound wave signal. So basically, we use a series of sign function or combination of a sign function to describe sound wave signal. So it should be quite straightforward. So, so sound wave is similar to the vibration signal, okay? Because the vibration signal may refer to anything, all right? But sound wave signal basically refer to the vibration of the pressure within the frequency range from 20 Hertz to 20 kilohertz, all right? So it's a subset of vibration signal. So you can say, okay, acoustic signal or sound wave signal is a subset of vibration signal. So therefore, you will see the application of a Fourier transform is quite important, right? So now we move on to the specific need for doing computation with the acoustic signal. Then after that, then we will focus our study on the measurement of the acoustic signal, right? So then here you may ask this question now. Why do we need to do computation with acoustic signal? The reason is this because of these two important scenarios. One scenario is for us to synthesize sound wave signal for whatever reason. For example, we want the robot to talk to us in a similar way like a human being. So how to enable a robot to speak out? Then we need to synthesize sound wave signal, right? Then how to synthesize sound wave signal? There are two ways. One is to make use of clone the example of phoneme in the spoken language. For example, in English, we have 44 phoneme, right? So if we have a sample signal, then by combining all these samples together, then we can create a computer. Okay, it's by doing computation. It's like a synthesis. Okay, come out the sound wave form or sound wave signal which correspond to the utterance. We use this keyword utterance of the sentence or utterance of the word, utterance of phrases, etc. Right? And another way is to do in-depth study, try to understand, okay, what should be the acoustic model when we pronounce A, B, C, D, okay, hello, good morning, good, bad, morning, afternoon, right? For each word, we do extensive study to come out what should be the set of sine wave function. When we put them together, we will produce A, B, C, D, okay, 26 letters, right? Then 0, 1, 2, 3, 4, 5, 6, etc. Right? So then we need to do a lot of study in this area. So these are the two ways for us, okay, to achieve this scenario of synthesized sound wave, which correspond to the utterance of sentence, utterance of phrases, utterance of a single word, right? So then when we put all the utterance together, then we have a speech, all right? And the second scenario is if let's say we have people who can speak standard or produce very standard utterance, okay, based on the input of the text, right? Then we can decompose the measuring the sound wave signal, then to identify the sine wave inside his or her utterance, okay, or eventually just to copy, okay, the phoneme exists inside his or her sound wave signal and store these things inside the database, okay, in order to support the task of synthesizing sound wave signal. All right, so these are the two typical scenarios in which we need to undertake the computation with the acoustic signal, right? So, and this drawing basically showing you the first scenario. For example, we have a text in mind. Now we want to let the robot to pronounce the text, but not us. For us, it's easier by reading the text. Then we can straightforward to speak out that. Then we need to know, okay, inside the text, we must do the decomposition. Decomposition the text into sentence into individual word. For individual word, we must decompose each word into phoneme. Once we reach the phoneme level, then we can put the sound wave signal corresponding to each individual phoneme. Then together, then we can create, okay, the final sound wave signal, right? So this is this scenario, okay? Second scenario is here, if let's say a person can speak a perfect, okay, utterance, right? And give this person a text, okay, then we speak perfect utterance. Then we need to do the decomposition, okay, to identify the way how to pronounce individual phoneme. Then we can store all this data into the database, okay? Later on we can use them to support synthesis of speech, right? So, and then from here you will see on Earth we have more than 100 over, okay, language. And then this will be a huge work, even for Chinese language, then other type of language, all right? So there are many phoneme, okay, in each language. For example, English has a 44 phoneme, okay? They are composed of, okay, they are consist of, okay, 19 consonant, okay, 7 digraph, okay, 5 are controlling the sound, and the 5 long vowels, okay, and the 5 short vowels, okay, and the 2 OO sound and the 2 deep tongue, okay. So you see there are 44 phoneme in English language, right? So So you see a lot of work, okay, for us to do, right? So once we have a database of phoneme or acoustic model, so you see this word acoustic model. So we need to have a database of phoneme or clone the example of phoneme or acoustic model for each phoneme, right? Then we can support, okay, the process of converting text into voice, all right? So then from this slide, then you understand that the post-processing gives the text as an input, decompose the text into sentence into individual word, each individual word into a set of phoneme, then retrieve the wave signal, okay, from the database, then combine them together, then come out the utterance of speech. You see this word, the utterance of speech, right? So these are the specific technical terms in the domain of speech recognition and text-to-voice synthesis, right? Then this video shows you a typical application, okay? Make use of multiple acoustic signal to support, okay, human-robot interaction with the use of human voice, right?
Prepare walking.
I understand that you say prepare walking. Confirm yes or no.
Yes.
Roger.
Prepare walking.
I'm doing it.
Walk forward.
I understand that you say walk forward. Confirm yes or no.
Yes.
Roger. I'm doing it.
Walk backward.
I understand that you say move backward. Confirm yes or no.
Yes.
Roger.
Walk backward.
I'm doing it.
Turn right.
I understand that you say turn right. Confirm yes or no.
Yes.
Roger. I'm doing it.
Stand up. Stand up.
I understand that you say stand up. Confirm yes or no.
Yes.
Roger.
Return to home
I'm
position.
doing it.
Detect object.
I understand that you say detect object. Confirm yes or no.
Yes.
What color is the object?
Red.
Detect read object. Confirm yes or no.
Yes.
I can approach the object by following the steps. Turn right 4.64 degrees, move forward 1.45 meters.
All right, so you see this is a typical demonstration, okay? And we have done this more than 14 years ago, right? So it's around the year 2008, right? And then here I'm going to showing you a example program in MATLAB for you to do practice. The good news to you is every one of you could download MATLAB for free because you are NTU student. Then with MATLAB and your laptop or desktop computer, actually you have a measurement system for acoustic signal, right? So you can follow this source code, and eventually you will see this result. So this is just a simulation for you to know how to combine sine function together in order to produce signal which looks like a sound wave, right? Signal, right? So here I just combine 3 sine function together, then the element together. Then you see the combined signal looks like this, all right? Is a series of bit, okay? So I let you to okay, play with this example program, right? So once you have okay, the sound wave signal, the second scenario is to decompose the sound signal into sine signal. Then how to do it? So during the lecture on measurement of a vibration, so you understand that the mathematical solution for us to use is what? Fourier transform, right? So then here we just take example. Example means to create a window. This window looks like a Gaussian distribution, okay? To take out this, we consider this as a sub-signal, okay? We create a series of sub-signal. For each sub-signal, we do FFT. Then, okay, for this sub-signal, then eventually we can identify a series of peak signal. Each peak signal corresponds to 1 sine function, right? Then for this signal, then we do FFT, then we see we have a peak signal, maybe eventually this is only 1, okay? Then for this example signal, we do FFT, fast Fourier transform, then we have a 1, 2, 3 peak signal, etc. Right? So for us to here more illustration now, you see a lot of series of sub-signal for each sub-signal. So basically use a Gaussian function to modulate the amplitude, right? Because if let's say we focus on the information at this point of time, then we smooth out the amplitude, okay, center it at the jumping time, all right? Then after that, we do the FFT. Then we see all these peak signal. Then each peak signal correspond to 1 sine function, all right? So then we have a series of sub signal, right? So this is just for you to know. And here I give you this example program for you to follow in order to know how to do FFT. So MATLAB give you this function of FFT bracket, okay? So once you have this synthesized signal, S is synthesized one, you calculate the length of the signal, okay? Then here we need to convert the length into a value which is power of 2, all right? So let me determine, this is a MATLAB function. What is the next power to this value, okay? What is the next? Then we use this to serve as a power, new power. You see, this is to compute 2 raised to the power of this value. And this is the power, okay, which will produce a number next to this one, okay? So next to this one, this is a function, okay? Find out what should be the power. If we compute 2 raised to this power, then that value will close, bigger and close to this input value, all right? Then we use this as the horizontal axis because this is to get the precision because FFT need to have this jumping number of jumper, which is value correspond to 2 raised to the power, right? So FFT, so this is the input signal, then this is the jumping time, okay? So the time, okay, axis, all right? Then we get the full data after FFT. Then this one is just to get the half of the data, because the full data will vary for the frequency, vary from 0 all the way to this number. Then when we vary from 1 to half of it, then we get the half of it. Okay, then we display the full output from FFT and the half of the output from FFT, because FFT will produce a symmetric output. So we just need to have a first half is good enough. All right. So then you will see this output. Okay. So this is the whole the frequency range. All right. So you see the symmetric. So we just consider half, and then half. Then you see this just these 3 peak. All right. So the range here is from 0 to 600 hertz. That is 0 from to 1,200 hertz. All right. So you can play with this with your computer and have a little bit okay hands-on experience with acoustic signal. Right. Okay, so that's about the computation. So you remember computation correspond to 2 scenarios. One is to synthesize voice as output. Second one is to decompose a sound wave signal into sub-signal, which correspond to maybe the phoneme, right? Or to determine the sign function, okay, inside each phoneme, right? So now come to the main focus of this lecture is to know how to measure acoustic signal, right? So we follow to convert sound wave is a pressure to convert the pressure wave into variation of inductance, right? Second principle is to convert sound wave into variation of a capacitance, and the third principle is to convert pressure wave directly into a voltage signal, right? So first principle, we'll make use of a coin plus the core inside the coin, because coin with the core, when the core vary, then inductance change. If we make use of a core inside the coin, which will produce a magnetic field, let's say permanent magnet, then we achieve 2 objectives. One is variation of inductance, another is to convert or produce variable magnetic flux. When magnetic flux change inside the coin, then it will produce current or produce voltage, right? So this is the first principle. Second principle is quite easier. If let's say we have fully charged the 2 parallel plates and let the one to move with a diaphragm, right? When the 2 plates are fully charged, when there's a vibration, then capacitance change because the charge is the same, Q is the same. Then when the distance okay change, that means the capacitance change, then it will produce a flow of electron in the closed circuit. So this is a way to convert vibration into the voltage. And principle 3 is to make use of piezoelectric material. Okay, the pressure wave act on the piezoelectric material, then it produces a voltage as output. All right. So all these 3 principles are familiar to us by now because we have already making use of them to support or to guide the design of other type of sensor. All right. So now I'm going through the detail with you. For example, how to apply principle 1 in order to design measurement and sensing system for acoustic signal. So therefore, you understand, okay, we will make use of a microcontroller because all microcontroller are digital sensor of voltage, right? If we can convert the value on the measurement into voltage, then done already, right? Then how to convert sound wave into voltage? If we make use of this principle 1, then we need to have 2 additional modules. The first one is to convert sound wave into variation of inductance. Second one is to convert variation of inductance into variation of voltage, right? Then how to convert sound wave into variation of inductance? The solution is to attach coin, because this coin is to pick up a voice signal. This is why we use adjective voice coin. Basically, it's a coin, okay, a light wave, because we know the pressure wave will not produce too big force. So then the coin must be light wave, okay, very, very light, attached to the diaphragm. When there's a sound wave, a diaphragm will vibrate, then the coin will vibrate. Okay, the coin will vibrate, and inside the coin we have a core, okay, metal core. Then that means the inductance change, okay. So when inductance change, then we can pick up an electric signal. But there's a clever design is to make use of a permanent magnet to serve as a core, okay, a core inside the coin, right? Then in this way, immediately we will produce a variable magnetic flux inside the coin. Then variable magnetic flux will produce voltage or current, right? So this is to convert sound wave into variation of inductance. Then how to convert variation of inductance into voltage signal? The answer is to use magnet, permanent magnet to serve as a core inside coin, right? Then when there's a vibration, magnetic flux will change. When there's a change of magnetic flux inside coin, it will produce electricity, all right? So then immediately you know, okay, voltage signal will come out, right? So then this video showing you implementation. Okay, so you get a product looks like this. This is a microphone, all right? Then inside you will see transformer is to amplify alternating voltage. You understand what is transformer? Transformer can scale down or scale up amplitude of alternating voltage, right? Then inside transducer head, you will see there's a voice coil plus permanent magnet core. You see there's a permanent magnet core, okay? And then there's a diaphragm, voice coil, okay? Magnet means permanent magnet, all right? Okay, so this is the typical design. It's quite simple, right? Then transformer is to amplify or balance, okay, or filter out the noise, right? All right, okay. Then how to apply the second principle in order to guide the design of a measurement and the sensor system for acoustic signal, right? Then in this case, we want to know how to transform waves, sound wave into capacitance, then capacitance into voltage. And then after that, then we apply microcontroller, which will be served as a digital sensor of voltage. So the additional two module will be the conversion from a sound wave to variation of a capacitance. Second module is to convert variation of a capacitance into variation of a voltage, right? And how to convert a sound wave into variation of a capacitance is quite straightforward. Capacitor is what? Capacitor consists of two parallel plates. Then we let the one plate to be movable and attach it together with a diaphragm or use diaphragm to serve as a movable plate. Then another one is a fixed, all right? Then we apply a constant voltage there. So the capacitor is fully charged, all right? When the distance change, then there will be a flow of electron, movement of an electron, okay, inside the closed circuit because we form a RC circuit, right? So when the distance change, capacitance change, right? When we fully charge the capacitor, form this RC circuit, a resistor capacitor circuit. Then when there's a change of a capacitance, then there's a flow of electron, right? So this is the way to convert variation of capacitance into variation of voltage, right? So then this video basically showing you the implementation.
The most common transducer types are dynamic and condenser. In a dynamic microphone, sound waves strike a thin plastic diaphragm and cause it to vibrate. A coil of wire attached to the back of the diaphragm vibrates along with it. As the coil moves back and forth, it passes through a magnetic field created by a magnet, which generates an electrical signal that corresponds to the sound. Dynamic microphones can handle even the loudest sounds without overloading, but this also means that they're not well suited to distant miking of quiet sources. Because the sound waves have to move the mass of the diaphragm and the voice coil, they usually have limited high-frequency detail, so they're better for vocals or horns than for stringed instruments. The size of the magnet makes it difficult to make a dynamic mic very small, which can limit your mounting options. In a condenser microphone, sound waves also strike a diaphragm and cause it to vibrate. The diaphragm is mounted just in front of an electrically charged plate. As the diaphragm moves back and forth, it changes the electric field between the diaphragm and plate, which generates an electrical signal that corresponds to the sound. Since there is no voice coil in a condenser mic, the sound waves only have to move the diaphragm. This gives condenser mics better high-frequency detail than dynamics. This makes them ideal for miking stringed instruments, percussion, piano, or subtle vocals. Condenser mics usually have higher output than dynamics, so they're good for distant or quiet sources. Since there's no magnet in a condenser mic, they can be made extremely small, which makes it easier to mount them in tight spots and make the mic less visible. Condenser microphones have internal circuitry that requires power to operate. Usually, phantom power is supplied through the microphone cable from the mixer or recorder.
That's how implement, okay, principle 2. Then how to apply principle 3 in order to guide the design of a measurement and a sensing system for acoustic signal. Then in this case, it's quite straightforward because sound wave is a pressure wave. When pressure wave applied or received by piezoelectric material, then the piezoelectric material will under compression or expansion, then that will create a voltage signal, all right? So it's quite straightforward, all right? So then in this case, you want to know how to convert a sound wave into a time signal of a voltage directly. So we know this principle already, okay? So we can design such a device which will receive acoustic wave. Acoustic wave is a pressure wave, all right? When the pressure wave applied to acoustic piezoelectric material, then the piezoelectric material will output current or voltage, okay? Then we can first amplify this signal, right? Then supply it to microcontroller, right? So this video showing you innovative implementation with this working principle.
High sensitivity and excellent speaker recognition. The self-powered flexible acoustic sensor was fabricated by mimicking the operating mechanism of the basilar membrane in human cochlea. While low-frequency sound vibrates the membrane near the base region, high-frequency sound induces the resonance in the apex region. The resonances occur at different frequencies of voice depending on the width of the multi-channel sensor membrane, which enables highly sensitive acoustic sensor. In addition, the flexible acoustic sensor can acquire abundant voice information from the multi-channel structure. This multi-channel acoustic sensor covers the entire voice frequency range, providing much higher sensitivity compared to the reference microphone. Conventional microphones exhibit limited recognition distance due to low sensitivity. However, the highly sensitive flexible acoustic sensor could detect minute sound from a farther distance. The flexible acoustic sensor demonstrated machine learning-based speaker recognition, determining who is speaking and what is said. Using flexible acoustic sensor with simple algorithm, the error rate of speaker recognition is significantly improved, which allows personal-based artificial intelligence service such as TV, refrigerator, AI secretary, and smart home appliance. This flexible acoustic sensor can be applied in the intuitive voice user interface based on customized individual communication and biometric authentication.
Right, so you see, this is a very innovative implementation. Okay, so this video show you one more implementation, which is also very, very innovative. Right.
Hello Indiegogo, we're Matrix Labs, an open source creation company consisting of a passionate team of 35, distributed around the world. We create versatile hardware and software which enable the convergence of IoT with artificial intelligence. We love creating and manufacturing revolutionary machine intelligent products, have shipped tens of thousands to over 50 countries, and have 2 successful crowdfunding campaigns under our belt. So what's next for us? Voice recognition. The only problem is that everything on the market is either too expensive, too complicated, or just not powerful enough. The best options are Amazon Echo and Google Home, but then you're locked into the respective services and things. That's why we're proud to introduce Matrix Voice,
the cheapest, most developer-friendly, and most powerful development board for voice applications. Matrix Voice is for makers. It's for industrial and home Internet of Things engineers, from novice to hardcore developers. Matrix Voice is powerful. Measuring 3.14 inches in diameter, it offers a radial array of 7 MEMS microphones, connected to a Xilinx Spartan 6 FPGA and 64 Mbit SD-RAM, which provides developers with the opportunity to integrate custom voice and other hardware-accelerated machine learning technology right onto the silicon. Matrix Voice also includes 18 RGBW LEDs, 64 GPIO pins for device-to-device connection, standalone 2.4 gigahertz Wi-Fi and Bluetooth-enabled 32 bits microcontroller version of Matrix Voice is also an option, satisfying the demand for mass commercialization of voice solutions for industrial and home IoT. You start by plugging Matrix Voice into a Raspberry Pi or other single-board computers, or by connecting it to power for standalone use. From there, you can download our CLI tool and libraries to start programming. We have made the libraries in multiple layers, so you can directly program the FPGA, or use C++ via HAL, or go all the way up to MOS and program everything in JavaScript with only a few lines of code. On top of all of that, we include technology for far-field voice capture, beamforming, acoustic source localization, noise suppression, de-reverberation, acoustic echo cancellation, and voice recognition integration with Google Voice and Amazon Alexa. Plus, our Matrix OS has a suite of computer vision algorithms, including face detection and gesture recognition, so that you can integrate some of the most advanced computer vision algorithms in the world by simply attaching a camera or Raspberry Pi. Matrix Voice came to life due to overwhelming demand from thousands of developers already part of our Matrix ecosystem, comprised of our own OS, App Store, and our Matrix and Matrix Creator products. Matrix is our consumer-focused, sensor-packed IoT hub, winner of the CES Innovation Award, and successfully funded on Kickstarter, shipping Q2 of this year. Matrix Creator is our Maker Faire Blue Ribbon Award-winning sensor-packed development board for the Raspberry Pi, successfully funded on Indiegogo. We have shipped tens of thousands globally and dubbed by Make Magazine as one of the most promising pieces of hardware.
Matrix Voice is for the do-it-yourself maker and enterprise developer. Everything is done. We just need to manufacture at scale so we can reach the affordable pricing of the board. Back us today, and together, let the world hear the voice of our creations. Thank you.
All right, so it's quite interesting implementation. It's quite innovative. All right. So the good news to you is with MATLAB and your desktop and laptop computer, actually you have a measurement and the sensing system for acoustic signal, right? So here I'm showing you this example source code. So MATLAB offer you this audio recorder. So then you just create an audio recorder, name it as a my recorder. Then you say you are going to record it for 8 seconds. This you can change. Then you say, I'm going to start to do the recording. Then you call this function, okay? Activate your recorder for this period of time. Then after that, you can get the recorded sound or data, get audio data from this recorder, all right? Then you can play back this recorded sound by calling this function. This is just playback, right? And then eventually you can display the recorded data. Okay, this is recorded sound. And the plot means the display, and you define the time window for you to observe the recorded data, right? Then this just to label the access, etc. Right? Then by running that program, you should be able to get result like this. Okay. Click run. So now I'm talking. Okay. And then you will record my voice.
Hello, welcome you back to study MA4822.
You see, this is my voice, right? So, okay, play with this one. Then after measurement and the sensing of acoustic signal, then you have a digital audio signal. Then that opens the door to many applications or many other studies, such as speech recognition, speech understanding, the voice-based control, whatever, conversational dialogue, machine translation is a big application, all right? And the voice-based inquiry system or answering system, all right? So this just for you to know, all right? And here just show you application scenario, okay?
Jasper, lighting. Which lights, your lordship? Illuminate. And the lights come
You see
on.
the light illuminate, okay? Yeah.
Jasper. Jasper. Lighting. Which lights, your lordship? Extinguish. Oh, well done, and the lights went out.
Okay. Then this flow chart basically is for you to know how to undertake cognition and the recognition with acoustic signal, all right? So for those of you, if you want to venture into advanced study or to do research, then these are the useful information for you to know, all right? So that's all for the study of this lecture. So the key takeaway from this lecture is for you to understand the basic physics and the mathematics behind acoustic signal in general and the audible acoustic signal in particular. And also the key takeaway include the two scenarios for you to undertake a computation with acoustic signal. One is to synthesize the voice. Another is to decompose the acoustic signal into sign function, which correspond to the composition of meaningful phoneme in the language, right? Then the main takeaway from this lecture should be the three principles for you to follow in order to guide the design of a measurement and the sensing system for acoustic signal or audible acoustic signal. Thank you for your attention. I'm looking forward to seeing you in the study of the next lecture.